So now I turn the floor over to Ian MacLeod, who's going to speak to us about magnetic vector inversion, a simple approach to the challenge of varying direction of rock magnetization. There you go, Ian.
Thank you very much, Edna and KEGS and everyone for organizing this. I do want to start out with, I do not own a distillery, so nobody should request bottles of kegs of anything from me. Ian MacLeod is the Scottish equivalent of John Smith, I think. It's a very, very common name. There's pages of us in the phone book. So anyway, thanks for that, Edna. Yeah, today I'm going to be talking about magnetic vector inversion, and so welcome everyone online who's interested in this subject. I do want to open with a few acknowledgments. First of all, my co-author is Rob Ellis, and Rob really led the science team in the development of the MVI technique as we've implemented it at Geosoft. He was also the lead author of the 2012 paper at the ACG that actually gives you the science behind MVI. This particular study is more how we're applying it in different areas and was for the purpose of a workshop we had at the ACG last year. So secondly, I do want to acknowledge the ACG who put together a really good workshop at the ACG conference last, I guess it was February, and it was, or sorry, September, and it was presented at the Forum on Remnants and Demagnetization, which you see in the bottom right corner. There were a lot of really good papers on how people are approaching the problem of remnants or the direction of magnetization not lining up with the Earth's field. So it was a pretty big step forward, and our contribution is what I'm going to show you today. I'd also like to acknowledge and thank many people at Geosoft and the teams at Geosoft. This particular piece of work required over 29 people at work, and we continue to evolve the technology and the service to help explorers everywhere. There's a lot of effort going behind this stuff. And I want to acknowledge the data sources. PIRSA, the primary industries and regional in regions of South Australia, provided data for the South Australia example I'm going to show. And Codamig in Brazil provided the data from the iron quadrilateral in Brazil. So it's anybody who gives papers like this, one of the real challenges is getting data and getting permissions. So it's important to be able to have people give us these things. So a quick outline. I'm going to first remind us of some basic but important properties of the magnetic field. A bit of Magnetics 101. I'm going to then explain how magnetic vector inversion works and show you how it behaves with synthetic data. And I'm going to compare it to a really well-studied remnantly magnetized intrusion in South Australia. Then I'm going to tackle a particularly thorny low-latitude problem in Brazil, which is the iron quadrilateral in Belo Horizonte. And then finally, in the section that I call Fun with MVI, I'm going to show you a couple of other useful things that we're doing with MVI. Just to get our brains thinking a little bit differently about what we can do and what's possible with this kind of data. So let's go back to Magnetics 101. Now one thing is this isn't even Magnetics 101. One of the things I love about the magnetic field method is that we all learned it in grade school when our teacher brought to school a magnet, a piece of paper, and some iron filings. And I'm pretty sure everybody in their first science class learned about geophysics just by doing this. And that's exactly what I did when I presented this, a bit of work with this for at the KEGS talk last year for Introduction to Geophysics. We handed out a magnet and everyone was able to do this and actually understand the magnetic field. And this is what magnetics is really about. So that seed was planted in all of us at grade 4 or 5 whenever we had that particular science class. And with this really simple model, we can see a magnet and the iron filings actually organize themselves around the magnetic field, and we're measuring that magnetic field, and that's kind of cool. Of course, in geophysics, what we're doing is we're taking something magnetic and we're putting it in the ground, in the earth. Of course, the earth is cut off at the earth-air interface, and so we have the air above, we have something buried in the earth, and we're dealing with this particular problem. And if I went across this and actually drew what the magnetic field vector looked like at a bunch of points here, any of us could easily come up and and decide how strong that magnetic field is by the length of that vector and its direction, just by looking at how the iron filings are lining up here. And that's all I did when I worked out what this thing would look like. So now I've come along as a geophysicist, and I'm going to measure that magnetic field, see what that magnetic field looks like in a magnetometer. And a magnetometer measures the total magnetic intensity. And the total magnetic intensity doesn't have direction. It has the whatever that total field is, which is the vector sum of the Earth's field together with that little red arrow that's going along there. Now at this point, I'd like to raise an objection. And this objection has been raised to me even when I gave the talk previously. They go, well, why is the Earth's field being brought in at this stage? And we're thinking of the Earth field only in the context of the measurement, not in the context of what it's done to the Earth. And you'll observe here quite intentionally, I've got this magnetic body in here pointing in a different direction than the Earth's field. Now, a fundamental thing we're doing with magnetic vector inversion is we're not concerning ourselves with why that magnetization is oriented that way. It could be oriented that way because of induced magnetization, anisotropy, demagnetization, or remnants. Any combination of those things will orient the vector how it's going to be oriented in the Earth, and we're measuring that response. And so with magnetic vector inversion, we don't concern ourselves with why that became magnetized the way it is. But we do know that the ability for rock to be magnetized is a proxy to the actual physical property of that rock. The more magnetically susceptible that rock is, the more ability it has to be magnetized. And that proxy is a useful thing when we're trying to figure out geology. More magnetic rocks have a different geologic imprint than less magnetic rocks. So with magnetic vector inversion, we're going right at the exact modeling that vector itself and not concerning ourselves with why that's magnetized the way it is. But it is important because when we measure the field, we are measuring in the presence of this field. And so when we look at this little vector here, we can see that that little point here lines up with this field, and so we'll get a small positive value. As we get closer to here, the horizontal expression of the anomalous vector causes this to get increasingly large. Right in the middle, just by deduction, I can see that the magnetic field is quite strong, but it's orthogonal here, so it's not really doing anything to the field. So I'm going to get a crossover. It's going to go through 0. Here the anomalous field is working against the Earth's field, so I'm going to get a strong negative, and then that negative will reduce and become a positive again over here. And I can do all of that without a computer. I can just do it in my head, just understanding basic physics. And with young geophysicists, I always recommend they actually do this. It's not about the computers, it's about how you think about things. And when you can't actually figure out what's going on with a magnetic anomaly, which has happened to me many times in my career, I just sat down with a pen and paper and I've thought about this and drawn out what I think things should look like just by thinking about it. And it's a very instructive thing to do. And of course, this is the kind of anomaly I would get in this particular scenario. All right, let's now pose the problem that we have in geophysics. What we actually know is what we've measured. So in this case, we have measured that that field curve like this. We know we have an Earth's field that's oriented this way. And the basic problem of modeling is to come up with a reasonable distribution of magnetization in the Earth that will explain what we've observed. What's become very common now is to break up the Earth into a bunch of cells. We do this in 3 dimensions into a voxel. And the basic question we're asking is, what is the magnetization in each of those cells that will fit the anomaly that I'm looking at? We are also faced with the reality that the solution is non-unique. There's an infinite number of solutions that will produce that magnetic field. But what we would like to do is come up with a solution that's reasonable, given what we understand about the geology, and reasonable what we understand about physics. And generally what we do feel is reasonable. It tends to be to have the body or have the magnetization distributed uniformly with depth, and that's something that you generally control with a thing called depth weighting. But typically we go, stuff has no particular depth bias, so we just want to distribute it evenly horizontally and vertically. The other thing that we do constrain is the horizontal gradient, that the magnetic field shouldn't change any more than it has to from cell to cell, so that the cells can hang together. So those are really the only two basic constraints you put into what's typically called an unconstrained inversion. In reality, unconstrained inversions don't exist. You've got to give some constraints, but those are the two minimal constraints. Now, if we pose that problem and then ask what is the magnetic distribution, what we would like to come up with is something that perhaps looks like this. The magnetic field outside of here or the magnetization is 0, so I have no vector, and in these cells I'm getting some vector response. And of course the best solution will actually line up with what problem we originally posed. And that's what we're doing when we're doing magnetic vector inversion, is simply inverting for these vector responses to give us the best possible fit, and allowing it to have the freedom to orient that vector however it is it needs to make the best response. So now let's go to a computer. We're now going to look at the synthetic problem. What we have here is a simple prism, a cube oriented in the ground, and we're going to assume we have an Earth field vertical, and we're going to assume a remnants, an actual remnants in the rock pointing off in this direction with a Koenigsberger ratio of 1.4, which means that it's remnantly magnetized 1.4 times the magnetization it would have by susceptibility in a vertical direction. And if I add those two vectors together, I will actually end up with a horizontal magnetization in the cube that looks like those little green arrows you see here. If I then measure the magnetic field at the surface, I will get a magnetic field, observed magnetic field that looks something like this. Strong high here, strong low here. The high makes sense if you think about those field lines moving out and away from here. When it goes up on this side, it's strongly pointing down, so it's adding to the Earth's field, hence this big positive. When the field lines propagate out from here and go up, it's strongly negative, hence this big negative. So this anomaly makes sense for this particular body. So now we have some synthetic data, and we'd like to now take this data and invert it and see what we get. And if we are able to invert the magnetic vector, we should get something that looks like the cube. And if we're not, we'll get something different. So let's look at this in section now. Here is the true model, the magnetic field pointing down. The effective magnetization of that cube is horizontal. If I take this data, the original data I just showed you, and I feed it into a conventional susceptibility inversion, that's an inversion where we assume that the only magnetization can be aligned with the Earth's field. You will get something that looks like this. Now this distribution of magnetization does exactly explain the anomaly we observed, but clearly it's not the model we started with. And not only that, it's not particularly geologically reasonable. And anyone who does inversion work with magnetic fields is often seen in this sort of situation where you get a low followed by, with a neighboring high, a strong gradient between them. And whenever you see that, that's telling you that you have a challenge with the magnetization direction. And this has been one of the criticisms, I believe, of 3D magnetic inversion early on, is that a lot of these things have been targeted as potentially interesting, when in fact they're in the wrong location. Another interesting thing to note here is typically when this happens, people deal with this problem by introducing a minimum susceptibility of 0. It's a technique called enforcing positivity. So you say, no, I can't have a negative susceptibility. Make my minimum 0. So explain this anomaly with only positive susceptibility. And that's what we've actually done here. You'll see the minimum here is at 0. And when you actually look at the data or the results, I find that it actually doesn't look that different. You just push this up and it's pushed this even stronger, and you get something that really hasn't advanced the problem very much. Now let's take the same data, we'll put it into the same inversion algorithm, but we'll allow the inversion algorithm to rotate the orientation of the magnetic vector to best fit all on its own. And if I do that, I get a result that we call MVI susceptibility. And in this case, you can see that it has oriented the vector sideways because it found it can get a better fit, a more natural fit by orienting it that way. We are getting the natural shape of the body. This does verify that it's fairly robust in being able to figure that out and get you a reasonable response. Another thing that we're introducing in this slide is the term MVI susceptibility. The units on the bar here are actually MVI susceptibility, and that's where we take the magnetization vector intensity and divide it by the total field to produce an effective susceptibility. The reason for doing that, it seems a little odd because if magnetization isn't caused by an inducing vector, then it's not truly susceptibility. But it turns out with the Kronosberger ratio and the way magnetic vectors move around and demagnetization, it's close enough within all the other approximations we do with magnetic field interpretation that it's useful. Not only that, as geophysicists, we're all trained to understand susceptibility now. We do susceptibility logging. There's lots of reasons to use susceptibility as the primary rock property. And so this allows us to take a magnetization vector and convert it to a susceptibility. And typically when people are working with this, they're usually modeling that or working with that amplitude of that MVI susceptibility. Okay, that's synthetic data. Synthetic data is wonderful because it's all mathematically perfect, and so it's typically not too challenging to get good results from synthetic data. So let's switch now to some real data. When we were invited to present at the ASCG, Dave Pratt suggested we have a look at this particular study area. It's the Black Hill Norite in South Australia. These are gabbroic intrusions that I can't remember the age of them. They're fairly young, but they this particular area has been studied in at least 6 papers, including this one, so it's really well known. They've also done coring and measured the magnetization direction, so it's really well known. Each of these, A, B, C, and D, are the identified gabbroic intrusions. You can also see that this thing is phased, that A, B, and C likely came in close to the same time, and at another time intrusion D came in, because clearly it has a magnetization direction different than the other ones. So here's a challenge. We know it's remnantly magnetized, and we'd like to figure out how to model that and get the best result. I'm showing first the analytic signal, and this really demonstrates why the analytic signal has become so popular and useful. It's such a simple thing. We're just measuring the amplitude of the gradient of the magnetization, and clearly the closer we are to magnetic things, the higher the amplitude of that gradient is. And so analytic signal nicely shows us the outlines of these things as simple highs. So whatever modeling we do, we feel should also agree fairly well with the obvious things that are being shown to us from analytic signal. All right, let's look at the susceptibility modeling first. So I took that data and I fed it into conventional susceptibility. And I'm saying model this data assuming that all the magnetization lines up with the magnetic field, which in this case has a declination of 8.4 and an inclination of minus 67 degrees. So it's not really steep, but it's off steep. And we can get a fit. In fact, the model from this data perfectly fits the data. In fact, I very rarely show you actually what these things look like because it exactly looks like the data. So we can produce a susceptibility model that will explain that. And in this case, it's producing these classic, I've taken a slice here at 1 kilometer depth through the model, very strong high and then these very strong lows. And so we get these pairs, and you get things like this that are actually quite distorted. So okay, it shows us there's some magnetic stuff, but it's getting things wrong because the assumption we've used is wrong. Let's look at what happens if you feed the same thing into MVI inversion. With magnetic vector inversion now we have MVI susceptibility. It's a simple scalar, so it can't be negative. It's only an amplitude. And now you see that the magnetic magnetization intensity is lining up together with what the interpretation is of the outlines of these intrusions. Now these black lines, by the way, are it's a contour of the analytic signal. I took an arbitrary contour that was sort of at the inflection point of the analytic signal to outline where I interpret the edges of these norites to be. So that's fairly reasonable. Here I'm plotting a cloud plot where we're plotting each inverted cell as a little cone, which shows the magnetization direction. And it's an interesting way to look at it where we start to bring in direction information because sometimes that can be helpful. And I'm going to show a bit more about that later. But I'm going to have a look at this anomaly C here because it was the subject of more study by all the other papers. This is the one that they knew the most about. So I'm pulling this out, and you'll see here how MVI has lined up the vectors. And in particular, I'm just looking at this centerpiece where it really has some consistency. And I'm going to actually pull that out and have a look at what the declination and inclination are from modeling. And it turns out that the MVI method is able to accurately determine the declination and inclination relative to the other works. So the most recent work was Pratt's paper where he modeled this carefully as an ellipsoid body with remnants. So by doing that, he came up with the declination inclination as shown here. MVI just by itself came up with this. Some of the other numbers that we had, the remnants that was actually measured in core was declination of 221 degrees. Now this is a little different than remnants because this is actually the remnants plus the induced effect, so don't get thrown off that it agreed exactly. But basically this lines up. And this was done with very little muss. We just allowed the thing to work. Now this challenges a dogma, I suggest, in our industry that I've had since I worked at PGW, where we actually were doing this kind of thing a long time ago with simple parameterized modeling. But the dogma that got in place at that time was you can't model remnants unless you've measured it. And what this technique shows is, in fact, you can invert for remnants. You don't need to measure it. And it turns out that this type of inversion technique is surprisingly robust in its ability to sort out the magnetization vector relative to what's actually going on. The other thing I want to point out here is that what I'm doing here is very little, in fact, almost nothing other than pushing a default inversion, which is a bit unfair because we actually recommend that people really run multiple inversions and think about the results. Because the non-uniqueness problem is real, and inversion isn't about just pushing a button and getting a result. Having said that, all the examples I've shown you were from one run. I fed it the data, pushed the button, and this is what I got. So that's how robust it is. There wasn't very much fussing to make that happen. Now, if I was in a real exploration play, I would want to now go back to the geology, compare it to this, look at the exceptions, put in constraints, think about making my model as explain everything that I can, but for the sake of this paper, it's just one result. Okay, now let's switch down to somewhere that I spent a lot of time when I was at PGW, was working in Brazil. And this is a great place to work with magnetics because it really teaches you the fallacy of magnetization is only by induction. Because down in Brazil, you very rarely found anomalies that were induced only. Everything was crooked. Everything was mixed up. It was really tough to make things work out. And it was in Brazil where I developed that technique of just drawing out magnetic fields on a piece of paper and thinking about why it is I'm getting an anomaly that looks like this. And I was regularly having to move that vector to make things make sense. So I thought we'd grab a really juicy example in Brazil. This is from the iron ore quadrilateral around Belo Horizonte in Minas Gerais. This region, this particular feature, has a production of about 160 million tons of iron ore a year. It's perhaps the largest or the second largest iron ore producing piece of ground on Earth. It's not really that important what all the geologic units are, but you can see it's a very old Archean banded iron formation. It's a quartz banded iron formation which took the name Itabarite, and Itabarite is actually named after a little town called Itabaro, I think. It's right around here. Jerry, you know it? Itabirito, I think it is, and then it's located right in there. Anyway, it's quartz banded iron formation, and I've drawn on from the geology this black line, which shows you the outline of the iron formation. And if you look on this map, you actually see a lot of these brown stains here. These are actually the iron ore mines. And if you've ever been down there, and I have, and driven along here, it's quite mountainous. You actually drive along a ridge here, and you just see mine after mine where they're mining out this Itabarite in this region. So that dashed line is going to be on every slide that you see from here on in for reference. You can always see where you are. The other really nice thing about this as a magnetic problem is you have this great east-west striking arm here. The magnetic field is fairly horizontal here, and so it's interacting with this feature directly. The field is cutting across this. And we've got these north-south arms that are lining up with the field. So we shouldn't expect to see much interaction with an inducing field along these. And the third thing it's got going for it as a challenge is it has a lot of topography. And that's another thing you learn when you're in a place like Brazil. Because the field is running horizontally, you're actually getting an anomaly from where that field is going in the backside of a mountain and coming out the front side of a mountain. And you get these little circles on the back sides and front sides of mountains. Unfortunately, in Canada, where a lot of the science of this stuff was done, we've got this nice vertical field where typically we don't worry about that stuff. But in Brazil, it's a really big deal. So I'm sure you're keen to see what the magnetic field looks like. This is the magnetic field data courtesy of Cotamig. And as expected for this east-west striking arm, first of all, you see that the Earth's field has a declination of -21. It's running up in this direction. A horrible direction for these features. And an inclination of -29. So let's think about this a little bit. This east-west feature is pretty much giving me what I would expect, a strong negative. It's the kind of anomaly you expect in Brazil. And I go, well, this sort of thing is okay. And then as I turn to north-south, I've got some problems. For one thing, with the magnetic field direction going this way, what I would actually expect for these north-south features is a positive anomaly, because I'm actually getting an interaction with the top of the body, but I'm not getting much with the sides. But in fact, the strongest response I'm getting is through these negatives, and that's lining up with the Itabarite. And my positive is offset to the side. Similarly over here, I go from a negative to a positive to a negative. So it's just a challenge.
Just curious, the flight height for that survey?
It would have been, Jerry, I don't actually know, but I believe it's about 150 meters. And I upper continued it to 250 meters. Sorry? Jerry asked me what the flying height was, so I would say it's effectively about 350 meters to 400 meters. Now, this is quite large scale. This is perhaps 40 kilometers across. Well, there's a scale of about 10 kilometers. So this is the kind of typical problem you get in Brazil is stuff that looks like this. And this is also, the first work we did in analytic signal was actually in Brazil with a gentleman named Sergio Vieira, who found that if he just did the amplitude of the gradients, he was getting a better lineup of the mag with the total field. And from that, we started thinking about analytic signal. And down in Brazil, boy, this is really helpful. So sure enough, the analytic signal correctly now really lines up well with that Itabarite, and even on the north-south things. we're getting this spottiness because the vector is going in and out of mountains and is interacting and not interacting with the atabarite, but we are showing correctly where things are. So that's another good reference. We have confidence in the analytic signal, and our model should also line up with that. See where I am here. Okay, this slide is showing you the observed TMI on the left, and on the right I'm actually showing you the model response. And I'm only going to show you one. I've run a model for susceptibility only, and I've run a model for MVI, and both of them will give me exactly this response. Things you'll notice is that the noise level is set to filter out this sort of background stuff, so it's quite smooth in this background, but it does adequately explain the observed data. So the inversions are giving me models that will explain what I've observed. So that's the non-uniqueness challenge, that all the models will explain what I've observed. You can't tell from that, so you've got to use other things to think about it. So first of all, just a simple cartoon. This is the conventional susceptibility. And what surprised me when I first ran this is even this east-west striking feature here was also giving me this challenge of a negative-positive pair. And the atabarite was actually closer to the negative than the positive. So even here it's wrong. And then as I rotate to come down here, the problem just exacerbates. So the conventional susceptibility was not useful in this case. It was not accurate in this case. If I model with the MVI susceptibility, and by the way, this is a depth slice just below the topography. So I've taken, I think, about 100 meters below the topography and sliced it through the model to give me these results. And so the MVI susceptibility correctly lines up with what I would expect the atabarite to be, and it agrees fairly well with the analytic signal. Again, this is another case where this was one run. I just let the thing run and give me the best fit it can, and this is what it gave me. So you'll also see I've got a couple of profiles here for reference. So we're now going to look at the A prime profile and the B prime profile. And I'll show these in 3D. I've just draped the geology on the topography on top here. I've actually drawn the atabarite here in this white line, faint white line you see running through here. And this is showing me a section of the conventional susceptibility. This is the strong positive, and then this negative here to reproduce the field that we had. And I'm also showing the cone vectors pointing in the direction of the inducing field. So the susceptibility model, which explains the data, looks like this, and it misses the location of the atabarite. It's close, it's down the middle here, but that's the deceiving part. Let's look at what MVI susceptibility did in 3 dimensions. Same, there's a shell here at the 0.2 susceptibility boundary, and you see now the vectors, it's allowed the vectors to kind of rotate their way around here, and this lines up spot on with the atabarite. In fact, you can even see a couple of the mines here. There's a little bit of shading here, where they're mining along the top of this mountain, and there's tailings going off the mountain for where they're doing the mining. Let's look at the other one, V prime. Now here's the more challenging one. We're going east-west with north-south trending geology. And on the right here, that red plus 0.2 and the blue minus 0.2 are the shells of what was modeled from conventional susceptibility. And then in the middle, you see what was modeled with MVI susceptibility. Has to work here. And again, it's lining up with the atabarite, which you can see is this trace coming through here. Okay, now if that wasn't enough fun, I thought I'd just throw a couple of extra things in here to Now that you're thinking about understanding that the magnetic field is a vector thing, we actually have the power now to figure out what that vector is. What else can we do with that? And I'm glad that hopefully Alan reads online, because I'm looking forward to hearing his. He isn't. I'm going to come up to his talk next week, because I've heard his talk, and I actually agree with him. I've been a reduction of the pole denier for pretty well all my career. I think it's a waste of time. That's why we came up with that analytic signal method over 20 years ago. It's kind of a holy grail. Every year you'll see papers in geophysics about reduction to the pole and a better algorithm, And all of us who are very experienced in geophysics know it's not about the algorithm. It's about the physics of the problem. You've actually got an unsolvable physical problem when you assume that the magnetization comes from induced magnetization, and you've got to rotate that vector to be vertical. It's actually impossible to do because of the non-uniqueness of being right at the pole. And it's actually at the pole where you need it, or sorry, at the equator. It's actually at the equator where you actually need it most. So that everyone's trying to figure out the best way to do that and give you a clean field at the pole. In this day and age of modeling, you ask, well, why would I even bother when I can just produce the model? I'll work with the model. But there's actually quite a few reasons to want to produce, say, a good Laplacian potential field dividing function at the pole. There's lots of other algorithms that people have that require a Laplacian function at the pole to behave nicely. And so there's many papers you'll still see where the first thing they do is reduce it to the pole before they feed it into their algorithm to get a better behavior out of it. So let's think about this problem now, reduction to the pole. Taking that Brazilian example, I'm showing you here on the left the conventional reduction to the pole as implemented by an algorithm used in MagMap. And Fraser Grant and the team working on MagMap in the 70s actually figured out how to dampen the amplitude component, which was the most troublesome part of the reduction of the pole, by using this fudge factor, which in this case I set to 40 degrees. And so it makes sure that the amplitude component doesn't blow up on you. It's a simple technique. The most common alternative method is a method called equivalent source. And on the right, I'm showing an equivalent source. Now, by the way, now I'm using the same data, the same approaches, same filtering, everything else, and you can see equivalent source is actually the same as MagMap. It hasn't really advanced the problem. And normally when I see people compare these things, what they're actually comparing is people have pre-processed the data differently, or they've handled the data differently. But the mathematics are still dealing with the same physical problem. This pole-reduced map is clearly not representative of the atabarite. You've now got distorted stuff that shows a high and this distorted low. You still have these stretching problems. I really think this is a bit of noise here, and this noise is stretching out. But this is sort of the best we have with reduction of the pole now. This approach for reduction of the pole assumes that magnetization is by induction only, and that's what we're rotating. Okay, let's say we took that MVI and we said, okay, I've calculated the susceptibility with allowing the vector to vary, and let's just take that susceptibility and let's pretend it's at the pole and calculate what the field would be at the pole. And what you get is that image on the right. And this is an MVI approach to RTP, where we removed one of the main problems with the physics of it, which is this assumption that the actual field is horizontal when in fact it's not. And so now you get a really nice clean RTP. And one other small bonus if you want it, because we have a noise level set on the model, it's also naturally filtered out these things. If you tighten up the noise level when you do the inversion, you could bring those kinds of things back. But now I've got a nice Laplacian function at the pole that I can then use in some other process, which is a much more realistic model. The other thing we have not solved here is non-uniqueness. We can't solve non-uniqueness. But this particular approach is similar to equivalent source, except that we've allowed the vector to change, and we've allowed the distribution of magnetization to extend down into the Earth. Equivalent source puts it all on one layer. You have to make one layer and give it all one value. And that's a real problem when you do a reduction of the pole, because everything's stuck on that layer, and then you've got a spatial problem. So that's the problem you saw before. Wasn't that fun? And that's the one I want Alan to challenge. Too bad he's out online because he's an advocate that this can't be done, and we feel, well, you can do it now with an approach like this. The other thing, and Carl, you inspired me in your talk last month with the neural networks, and as Carl explained very well last month, there's a few approaches to neural networks, but one of the ones that Carl didn't talk about was this technique called self-organizing maps. And in self-organizing maps, you're basically taking multivariate data of any kind, and you're asking the data to organize itself into distributed classifications that are as different from each other as they can be. And so the self-organizing nature of it is it just, you feed it all the data in a multivariate sense, and it will organize itself into these classifications to be as different from each other as possible, and you get a set of classifications. So the neat thing with MVI is I've now got multivariate, an interesting little multivariate set. I've got an amplitude, and I've got a magnetization in the x direction, the y direction, and the z direction. So I've got four variables. And let's see what happens if I give that to a SOM and say, well, look, organize yourself around this data and give me the classifications. Now, what I would expect is generally all the geology will then fall into, the magnetization directions will then bucket themselves into sort of dominant fields of magnetization. But the stuff that I'm interested in is the stuff that doesn't fit that very well. So a little wrinkle that we've added is we're saying, okay, organize yourself around all the basic data, but give me the top 5% that's as far away from the other classifications as possible, which is the true definition of anomalous. Give me those values that are anomalous relative to the background geology, because typically that's the interesting stuff. So all I've done here is I've taken the MVI results, I've fed them into SOM, clipped off the 5%, and I've reclassified that top 5% into bins. And now I'm going to show you what I get. So, sorry, first of all, this is a point cloud of the magnetization vectors, just to give you an idea of the density of the information we have. So these are each of the individual vectors in the ground as MVI modeled them. And you can see they're color-coded, so the lowest ones are in green and the highest ones are in those pink colors. So I'm going to feed it all this data. There's about 700,000 points of multivariate data. Just fed it into the SOM. And with amplitude X, Y, and Z, the 5% that doesn't fit, I get this. And it right away just pulls out those features that I was actually interested in. And I didn't do anything fancy here. I just said, give me the 5% that doesn't fit and show it to me on a map. And we've done this on a number of different models that are interesting models, and every time it always gives me this stuff that doesn't fit the rest of the geology is my anomalous stuff, and it turns out that's the stuff that's interesting from a minerals perspective. It's a nice, simple technique to show me the interesting stuff. Now the other thing I can do is it's overly biased with amplitude, so I've also run it just based on direction. Same idea, direction only, and this is still, there is an intensity with the direction, but it gives me a slightly different picture. But the colors here, by the way, are only there for classifications. So I'm getting different classifications of the vector direction based on that. So that's a little bit of simple SOM analysis. Thank you, Carl, for the inspiration last month. And it's simple stuff you can now start to do with your data when you're thinking about what's going on. You could also go back to your original classifications and use those to help you with your mapping classification to see which of those domains are proxies for geology, which is a more conventional approach to this sort of analysis. So I'd just like to close with a few summary statements. They're not really conclusions, they're just position statements from our perspective. We suggest that inverting for the magnetic vector direction and intensity is straightforward, it works, and it is useful. We believe it's the best thing to do in most cases, and in all cases where the direction of magnetization in the rock is different from the Earth's field. In fact, if you aren't doing this, we believe you're making a mistake. It's particularly powerful at mid and low latitudes, which this is where the remnants and magnetization direction problem generally jumps out the most. We believe it's an elegant and robust method to reduce magnetic measurements to the pole. So it solves the RTP problem. And it provides additional information in the vector component, which we can then usefully use to classify magnetic rocks. And we demonstrated that with that simple SOM example. Thank you very much.
Thank you very much, Ian. Any questions? First, maybe in the room? And if Ian, if you could repeat the question.
Sure. Jerry first.
Thank you for a very elegant exposition, reminding me of, and probably many others, of the intricate aspects of magnetic interpretation and magnetization. In my simple earlier days, I thought of remnants effect simply as a reorientation of the magnetic vector, effect of magnetization. So that was one simple way out of the box, even simpler than yours. I guess in regions like Brazil, I favor reduction to the equator rather than the pole, much smaller transformation. And I think I would have been helped if you'd shown the total magnetic intensity profiles and the transform, the MPI, for those examples from Brazil.
Okay, thanks, Jerry. Sorry, I don't want to repeat all the comments. Did you have a question?
Oh, that was,
okay. Just in comment to the, it would be nice to see the profiles. The reason I showed the image is that the profiles match exactly. So it's more a trust issue. You can trust me that the profiles match exactly, which these inversions will produce the magnetic field that's measured, and that's just the way they work. But had I shown them, you would have seen a perfect match. Carl?
Yes, Ian, thank you. I just have a couple questions. It's Carl from Geotech. I wrote it down, questions here from my colleagues.
Okay.
So first question is, we're interested in inverting Mag 3DO MVI for large areas, countryside, like Cameroon or Niger, large areas. We have to do it in pieces. So the inverted balls, we have 10, 20, bunch of them. They each have different base level for susceptibility. You know, those balls. We have to merge them. So that's a task in itself. So right now, Geosoft simply merged the balls. So after the merging, simple merging, they still see artifacts along boundary.
Sure.
And we're wondering if there's Geosoft going to do something about it, like writing tools like grid stitching, like similar to grid stitch, balls of stitch. That kind of adjusting, automatic adjustment levels for each ball and then merge small balls into big ones. That's the first question. And,
okay, let me deal with that one first. I'm going to be careful. It's not. I didn't really want this to be too much of a software and what Geosoft does, but in the science of MVI, it is an interesting problem, and it can be very. Sorry to repeat the question. The question is how to approach large-scale inversions, countrywide, large regional inversions, where it would be useful to have a 3D inversion using something like MVI. Now, I don't think it's limited to MVI. It's really anything you're inverting. So how we think that through. And there are basically two approaches. One is for us to continue to expand the size of the inversion so you can just run it all at once. That would be the ideal. And I know we are working very hard on that because we have access to so much computing power in the core or in the cloud that we have the potential. What we ideally would like to do is be able to just give us the country and it will do the inversion for you. Short of that, you do have to tile, so break it up into pieces with an overlap, and then you have the challenges that you pointed out. We do have people using a tiling approach now, but they have to feather those things out. My own experience with tiling was always to have a 100% overlap, so every tile is exactly overlapping 50% of the next tile, So I've got double coverage everywhere, and then a pure cosine roll-off between the tiles. We don't have that implemented in the software, but it's something you can implement with an algorithm just by doing it with voxel math. And then if you get 100% overlap and use a cosine roll-off between tiles, you will not have any seams at all. It'll do it. It's pretty well seamless. Yes.
Nick Cook from Finland says, hi, we have a question. We have very strong remanents with Kongsberger ratios of 400. Yes, very high. And we wish to separate them from magnetite bearing and phibolites. The mineralization contains magnetite and pyrrhotite with gold. Any hints are appreciated.
I've never heard of Kongsberger ratios that high, but that's, Nick said that he's got challenges.
It says latitude is
66. So he's in mid-latitude, 66 north. He has very renally magnetized Kongsberger ratio of 400. My suggestion is use MVI to sort that out. I would beware that, or if I got into this, have a look at what the volume of the rock is, which isn't necessarily in the question. But I'd be surprised if you can get 400 Kongsberger ratio over any volume of rock. It may be that they've got a very narrow feature in there that's extremely magnetic. Now, once you get into things like MVI inversion, if you are, or any inversion, if you're dealing with quite narrow features spatially, you're going to be fuzzy. And all these techniques will broaden them out because they don't have the fidelity to see them. So to the question, do I have any advice? My advice would be take your data, make it as clean as possible, and try voxel inversion with MVI and think about what it's telling you.
May I read the next question then? This is Ekin Book, Akami, not sure where from. He says, can you explain the analytic signal map for locations in Brazil? What do those peaks mean?
Yeah, analytic signal is actually really simple. Mathematically, it's the sum of the gradients in the x, y, and z direction, just with simple Pythagoras. You square them, sum them, take the square root, and what you have is an intensity of magnetic field gradient. If you think about that, it's a really simple concept. What that means is the closer I am to something magnetic, the stronger that gradient is. And so if I'm right over top of it, I'm going to have a peak. As I move away from something magnetic, it goes down. And that's why analytic signal works. It removes the vector component because it doesn't care about the vector. It's a simple scalar value. There are some drawbacks to that. One drawback is it's very sensitive to things at the surface because it's only dealing with the gradients. You can, of course, do it with the total field and then calculate the horizontal fields. I haven't seen that done very much because I think the processing is problematic. And so when you saw the vertical, the reduced to the pole map, the reduced to the pole with MVI looked a lot more depth interesting than the analytic signal. And that's because it's more sensitive to things at depth. Analytic signal is very sensitive to things at the surface. Secondly, the analytic signal is not a scalar, it's not a Laplace field. You can't deal with it in any potential field way. It's a simple number. And so it's useful for mapping, but beyond mapping, there's not a lot you can do with it. We did a paper in 1993 that explains how you can get depth from analytic signal, but it's in practice, I don't think anyone's using that technique.
Next question from online. Your screen went off. Paul Schwering, he says, you mentioned MVI is most effective in mid-low latitude. What happens at higher latitudes?
The question is what happens at higher latitudes. That's a really good question because it also goes along with the question of how does MVI behave when you actually do have magnetization by induction only. If you do know that you have magnetization by induction, you actually have another constraint. You're more constraining the model. You're saying the model must be aligned with this magnetic field direction. And in that case, modeling susceptibility will give you a more accurate result because the assumption is correct. What MVI will tend to do is broaden things out. It kind of washes things out because it has the freedom to move that vector. then as for things at northern latitudes, if you have remnants or if you have magnetization that isn't aligned, it's going to work just as well in northern latitudes as at the equator. Now, I also have a personal theory. One of the reasons I believe we have gotten away with thinking that most magnetization is by induction is because a lot of the initial science for this stuff was done right here at U of T in northern latitudes. And we have this, we have a vertical field, and we have generally steeply dipping geology. And so the vertical field lines up with the steeply dipping geology, and anisotropy is a very strong effect. And typically the magnetic field will rotate to line up with the bedding, depending on how the mineral filaments are in the geology. So we tend not to see it very much at northern latitudes, because the geology is lining up with the field, and we don't really notice. You get down into southern latitudes like Brazil, the geology is still steep. The magnetic vector is going in sideways, and it's rotating when it gets inside the body and giving us a bigger problem. So to the question, it works just as well, but the problem is not as acute in northern latitudes. Jared?
Can I resume? The reason I raised the point about the profiles is on your data from Brazil, you indeed had an upward continuum, so therefore lost quite a bit of the original resolution in the data, I suspect. And I think it would be an interesting exercise to repeat your MVI analysis on the original data, which are probably contain multiple sources in some of these things that appear to be generalized single sources. And additionally, I note that part of the iron formation is not particularly magnetic, suggesting, of course, that quite acceptably the susceptibility does vary along the strike.
Yeah, I agree with all that. Yep. Jerry suggested it would be interesting to look at the data in more detail, and absolutely. For the purpose of the talk, we're trying to make this point, but if I were actually studying this from a geologic interpretation point of view, I'd be doing a lot more work, exactly as you're suggesting. I do want to suggest, though, that when you're doing inversion, something that's often not really appreciated is the importance to have spatial fidelity relative to the model you're dealing with. So some of these surveys, they tend to have fairly wide line separation. So for example, you've got a challenge if you go right down to the original observed data where you're quite close to the magnetic sources along these lines, but you've got nothing to control the inversion in between lines because you have nothing sampled there. This is a real physics and math problem. I have nothing to control it. And so what the inversions will tend to do is make things up in there to help explain things down the lines. And anyone who's worked with that sort of data has often seen stripes and all kinds of artifacts. The data down the line fits perfectly, but in between it's not reasonable. So I do recommend an approach for those things is to introduce data between the lines. Upper continuation helps, getting a little bit further away from the data, but also gridding the data and introducing some reasonable controls between the lines. So you do have to think about your data, think about your spatial sampling, and do the kinds of thing you're recommending, Jerry. Is, you know, if you're going to go into this with more than just give a talk, is you want to work the data more. Thank you. Okay, Steve.
First, a comment on reduction to equator. That will, in this kind of situation, it will reduce the north-south signal quite dramatically. So you end up losing some of that resolution of your data. Whereas RGP will keep, as you say, preserve the noise unless you have another better technique that you've shown us. The question is on dipping bodies, shallow dipping bodies. Is there any way, does MVI resolve dip from remnants direction?
The question is, does MVI, how does MVI deal with shallow dipping bodies, and is it able to resolve dip? Actually, this is from my years of doing a lot of this at PGW. This was one of the areas that my own prejudice thought that it would not be able to do this. And I'm going to just show you an example here. This, this AA prime, there's a lot of dip measurements here. This is known to be dipping to the north at anywhere from 65 degrees to 85 degrees to the north. And the MVI, in this particular case, is showing a north dipping feature lining up with that. Now, it's not shallow dipping, but in the modeling I've done, it's been surprisingly good at picking up dips of things. The 2012 paper, which you can get online, shows a similar agreement with the Osborne deposit in Australia, where it was able to pick up the dip of that feature. Now, having said that, you have to remember that the non-uniqueness still applies. So the depth regularization we're using here is a uniform depth regularization. So we want things to be as distributed in depth as they are sideways. If you change the depth, or sorry, not regular, change the depth weighting to say I'd like things to be shallower, it'll push things up shallower, so things will look like they're more shallow dipping. If you want things to be vertically dipping, you can just change that weighting to make them vertically dipping, and things will go vertical dipping. So we have a fidelity reality is that you can't actually tell. So if you use this sort of default and the geology is kind of amorphous, it's not too bad. But you don't actually know. So the magnetic field suffers from that problem. Now when we did parameterized modeling, as in the days of MacLeod, that was just one of the parameters, so it would fit things. And I remember in those days we did introduce remnants, and we found that something like a parameterized model like MacLeod would always trade off dip for remnants. You introduce remnants, it'll whack the remnants over there and the dip will go that way. And that's another thing that shows that the data kit has a real hard time figuring that out. But all that said, I've been pretty impressed with real cases where it seems to work quite, it's useful.
Yeah, maybe the three-dimensionality problem helps.
I agree.
In that sense.
Thank you very much. Oh, sorry, Carl had one more question. I was waiting here.
Again, from geotech, from my coworkers, it's not related to MVI, but related to voxel. So is Geosoft, when we going to roll out voxel 3D for time to medium inversion?
Don't know, Carl. We are.
Future?
Well, time is a long period. I don't know. We are bringing out a frequency domain EM inversion this year.
Okay.
So for DigEm style data, and it uses a quasi 1D type inversion that accounts for topography and whatnot. It works very well. But our long-term intention with the technology is to we're going to keep working at more and more techniques being brought in. At some point, I would expect time domain.
Okay.
All right.
Okay.
Thank you very much again. Thanks everybody online.
Yeah, thank you very much, Ian. And that would be it. That'll be it for today's meeting. And remember, Friday, June 6th, Dr. Alan Reed will be giving our talk. See you next month.
Again, a little bit earlier.